A chart is a marine map. Helps you find your way on the water. Charts help the mariner do many things from crossing large oceans to entering small harbors. Selecting the proper chart is an essential part of safe navigation. Charts range from an entire ocean or the world to a single small harbor. A large-scale chart equals large details with a small area shown. A small-scale chart equals small details with a large area shown. A Port Angeles harbor chart at 1 to 10,000 is a larger scale than a chart of the Strait of Georgia and the Strait of Juan de Fuca at 1 to 200,000. Caution is required when using any chart or navigation system. The chart you're using might not be up to date. An aid to navigation may have been moved or removed either by accident or on purpose, or the water depth might have changed due to local shoaling or other activities or dredging. Charts should be kept up to date using the local notice to mariners. Let's look San Diego, the Aleutian Islands, and Hawaiian Islands. This is a very wide area. It's for offshore navigation only. And there's no details for the Strait of Juan de Fuca. Moving a little more detail to the Gulf of Alaska, Strait of Juan de Fuca to Kodiak Island. Still offshore only. No detail is given for the Strait of Juan de Fuca, but we are given a chart number for the Straits of Juan de Fuca. Now the Strait of Georgia, Strait of Juan de Fuca, now showing detail in close to shore, and navigation aids are now visible. But there's no detail for Port Angeles. However, we are given a chart number if we want to enter Port Angeles. The Strait of Juan de Fuca, just the eastern part, has more details. It does have some details in Port Angeles, and again a chart number is given if we want more detail. And we now know that there's about 17 fathoms or about 100 feet of water in the center of Port Angeles. If we look at the Port Angeles harbor chart itself, much more detail, including shore objects and information on the marina. So let's go back and look at the Strait of Juan de Fuca, the eastern part of the chart, and take a look at some of the information that's available. We'll start with the title block. We have the chart name, we have the area that's covered, soundings in fathoms. 1 fathom equals 6 feet. Remember, fathoms, feet, or meters. We're also given the datum. Some charts will show you the depth scale in the margins, in this case fathoms. The entire chart is seaward of the Colregs demarcation line, and that means that international rules of the road apply to the entire area of the chart. For measuring distance, you can use the scale provided, or 1 nautical mile equals 1 minute of latitude equals 6,000 feet or 2,000 yards for many calculations. 6,076 feet is the international treaty for a nautical mile, by the way. Remember, miles for latitude, not longitude. Many people make this mistake. Other charts are shown that we can use the chart numbers if we want more details. This tells when the depths were done and how the depths were done. Some were done pre-1900 with the lead line, and many of the depths were pre-1940. We have tide ranges for selected points. If you don't have a tide chart, this can help you determine how much road or minimum water, because you can know the tide range, so the water could go down that tide range, so you need to have that amount of water under your boat. Or if the tide range comes in, the water rises, you need road for the deeper water. We have 4 compass roses on this chart. You want to use the closest compass rose to where your course is. Sometimes there's significant difference from one compass rose to the other. True north is shown on the outside, has the star on it. The inside is magnetic, which points to the magnetic north. The variation on this chart is about 17 degrees east.
The ECDIS system is only one of many complicated modern electronic navigation aids found on today's modern ship bridge, which a navigator is expected to handle in an efficient, safe and professional way. In order to do so, the navigator must have a good theoretical navigational background, sufficient navigational practice, theoretical knowledge about the ECDIS system architecture, functions and features, practical experience in the use of ECDIS systems. An ECDIS system is a very impressive system, even when seen through the eyes of a professional navigator. But no navigator should ever forget that all systems do have limitations, and the fact that these limitations are very often well hidden and or not mentioned in the system manuals. The most important thing to know about modern computerized systems is their limitations. Knowledge concerning their functions and features is quickly accessible, with a little interest and practice. The only way to get to know the limitations of a system is to study available material about the subject, system manuals, and by practical use under safe conditions. The Seafarer's Training, Certification and Watch-Keeping Code does not specify any special training in the use of ECDIS. STCW Table A21 considers the ECDIS training to be a part of the training in understanding a chart. As a modern ECDIS system is just as complicated as an ARPA, this lack of detailed training requirements may pose a hazard to ships sailing with ECDIS operated by untrained navigators. The reduction of presented information or proper selection of only relevant information is often an important task when setting up an ECDIS system. An ECDIS system which simultaneously presents all available information tends to be overloaded, and therefore important information may be cluttered and less visible. A basic and very important thing to understand and take into account at all times when using ECDIS is the fact that no system is better than the weakest chain. That is, rubbish in, rubbish out. Vital information for any ECDIS system is own ship's position. Whenever own ship position is wrong, ECDIS chart information is wrong. Simple as that. ECDIS systems accept position input from a number of positioning devices, as well as dead reckoning. Most ECDIS systems today are connected to a GPS and/or DGPS. This means that stable and good positioning can be expected most of the time. However, the navigator should never forget to check his position as often as practicable by all available means, in order to detect any malfunction or inaccuracies in the navigation system used as input to the ECDIS. Positions are always referenced to something. This something is referred to as the chart datum, and there are hundreds of different chart datums around. This means that the navigator at all times must know what chart datum does the ship's positioning system connected to the ECDIS use. What chart datum does the actual ECDIS chart use? Whenever the datum used by the positioning system and the chart are different, known corrections must be taken into account. Today, the ECDIS system is often connected to an integrated bridge system, or forms a part of an integrated bridge system, i.e. a system where the radar, ARPA, autopilot, positioning, routing, log, gyro, ECDIS, etc. are connected and work as one system. Several options for automatic sailing become available to the navigator. Depending on the ship position, that is open sea, coastal or restricted waters, the navigator may select between several sailing options. Here are some examples of possible sailing options found on an integrated ship bridge system. Course mode, Great Circle or Rumline sailing. Corrected course mode. Track mode. Course mode is a sailing mode normally used in open waters and for long-distance sailing, as this mode will give the shortest distance between 2 points. No correction for offset is made, but the ship will home to the destination. Corrected course mode is used in waters where it is necessary to correct for wind and current. Correction for offset is made, but no attempt to follow the original planned track is made. In track mode, the system will calculate the optimal path back to the original planned track. Track mode is used in restricted waters whenever it is important to stay exactly on the planned track. For a professional navigator, it's a matter of course that the route selected for actual sailing is properly checked before it's activated and used for actual sailing. Parameters used when planning the route must still be valid in order to maintain required safety margins. If not, the route may have to be changed before it can be used safely. Examples of parameters which may have changed after the selected route was programmed are ship draft, available position accuracy, engine reliability, steering gear reliability, etc. Navigation with an ECDIS system, especially when the ECDIS is connected to an integrated bridge system, changes the work situation for the navigator a lot. Conventional navigation with manual plotting of ship position in the chart, heavy traffic, manual course change in restricted waters is a task that puts a heavy workload on the navigator. A good working ECDIS reduces the navigator's workload a lot, especially when connected to a properly working integrated system. Then the navigator's role is more or less changed from actually doing the various tasks to monitoring these tasks. Seen from a safety point of view, this should be very good, since it gives the navigator more time to check important parameters and monitor the traffic more closely. Sailing with ECDIS requires a highly qualified navigator with a sound and positive skepticism towards computerized systems. ECDIS systems used by unqualified and/or untrained navigators who believe everything presented by the ECDIS will surely cause a number of groundings in the future. Take the necessary time and effort to really get to know your ECDIS. This will definitely save you a lot of work and trouble in the future. It may someday save your career or even your life.
Admiralty ENP Reader provides viewing of ENPs present on the PC. The Bookshelf page provides a tiled view of the ENPs, categorized into 3 tiles: All Publications, Favorites, and Recent. Click on the All Publications tile to expand it. A list of tiles is displayed with each tile representing an ENP. At the top of the list of tiles are the ENPs which have a valid permit, followed by ENPs which exist in the product catalogue and have not yet been purchased. Tiles with a permit are differentiated by a darker navy blue background colour. They also have a Favorites star and an expander triangle. Additionally, they can be clicked on when the mouse is moved over the tile, and the tile color will change to light blue, indicating that the tile is clickable. Click on an ENP tile you have purchased. The View Book page is then displayed. Each open ENP is displayed in a tab within the View Book docking container. These tabs can be left-clicked and moved around to allow for different view configurations. 2 books can be opened side by side, or in the case of multiple monitors, books can be dragged onto the second monitor. The ENP is shown with bookmarks displayed in the left-hand column, the ENP itself in the center column, and notices to mariners in the right-hand column. The light blue splitter dividing these columns and also the splitter to the right of the navigation bar can be left-clicked and dragged to resize the columns. The bookmarks within the ENP are displayed in a scrollable tree view. These can be expanded and collapsed by clicking on the expander arrows. Hovering the mouse over the bookmark text will change the background color to light blue, indicating that it is clickable. Clicking a bookmark will navigate the ENP to the page containing the bookmark. The ENP book can be navigated using the scroll bar to the right, by using the keyboard arrows, or by using the mouse scroll wheel. Along the top of each tab container is the toolbar for the ENP. Hovering over each of the toolbar buttons will display a tooltip describing the button functionality. The toolbar supports navigation through the book using the up and down arrows and by typing the page label into the Go To Page text box and pressing the return key. If notices to mariners have been issued for the ENP, they will be shown in the right-hand column. They are displayed in a scrollable list and can be collapsed and expanded using the expander arrow. Hovering the mouse over the Notice to Mariner title will change the background color to light blue, indicating that it is clickable. Click on the title. The main book view will navigate to the page containing the first occurrence of Notice to Mariner. A highlight border will be displayed around both the Notice to Mariner and the book view. The text, NMs have been published for this page, will be displayed at the top of the page. If an addendum exists for a Notice to Mariner, a button titled Open Addendum is displayed at the bottom right corner. Click this button to open the addendum. This will display in its own tab container. The toolbar has a combo box which allows for different zoom and fit-to-page attributes to be applied. To the right of the zoom combo box are the Fit Visible, Fit Width, and Fit Height buttons. The toolbar has Rotate Left and Rotate Right buttons to allow the current page to be rotated. This is particularly useful for viewing charts or tables which are displayed in landscape page orientation. The book view supports single or double page views. The toolbar contains 2 toggle buttons to switch between single page and double page views. The Camera toolbar button will open the page that you are looking at in a PDF format. This may take a few seconds to generate. The page will be shown with a watermark and will include the ENP number and the vessel name. If any NMs have been applied to the current page, these will also be generated on a separate page, as well as a third page if an addendum has been applied. Clicking the Save button will open a pop-up window, and you will be able to select a location to save the snapshot to. Click OK to continue. This can be later used to copy and paste into passage plans. If you have a printer connected to your PC, selecting the Print button will send the pages to your printer. Clicking the blue arrow will return you to the View Book page. The toolbar has a Search Book text box. Type the search term into this and press the Return key on the keyboard, or click on the Search Current Page button immediately to the right of the text box. This will search through the current page and apply a blue highlight to any matches of the search term. Click on the Search Previous or Search Next toolbar buttons to search through the book for the next occurrence of the search term. The book will navigate to the next page containing the search term with the matches highlighted. If no more occurrences of the search term are found, a message box is displayed. If the width of the tab container is insufficient to display all of the toolbar buttons, the expander arrow to the right of the toolbar will be enabled. Click on this and the remaining toolbar buttons will be displayed in a pop-up.
Basically, an ARPA is a computerized radar plotting system, which can perform radar plotting manually or automatically according to the operator's choice. ARPA is an abbreviation for Automatic Radar Plotting Aid. Computer-based radar systems have been used on board naval vessels since the 1950s. but not until the 1960s did system use come onto the market. These systems were more economical technology and good business. Navigators welcomed computer-based systems but lacked proper training, lay presentations. MO has requirements on the equipment and use of ARPA. From conventional radar to ARPA, the pre- and post-radar can expect some of the same problems. Thorough training is not received. There is a fantastic tool in the hand. Proper training. Personnel, it is a danger that operates. Since the first computer radar system came onto the market, many different ways of produced and delivered. Today, regardless of graphic presentation, all ARPA systems must be able to present target information in form of both relative and vectors should be time adjustable graphically. All ARPAs also display target separate screen. In addition, a number of graphical targets indicating navigation marks routes, pointing out targets that cause alarms, etc. A list of standard ARPA symbols can be found in the IECM Marine Automatic Radar Plotting Aids list. TV, True Speed Vector, indicates the target's speed and course. RV, Relative Speed Vector, indicates target's relative course and speed. TH, Track History, should be provided on request, consisting of at least 4 equally spaced past positions of the echo. PPC, Point of Possible Collision, is the point at which a collision could take place. PAD, Predicted Area of Danger, is the area to be avoided based on CPA and TCPA settings and relative target speed. Most ARPA systems manual acquisition, automatic acquisition. An operator, by the use of a point, and presses a button to time and position. A few minutes later, position the symbol on top of the echo again. Calculate target information, vector or other symbol. Use of a pointing device, echo, and presses the manual. After some time, normally less than 60 seconds, the operator is presented with the calculated target information. Before an ARPA can be operated in automatic acquisition mode, the search criteria must be specified. Today's ARPAs as the guard ring search area philosophy that most ARPA assist smaller echoes in manual acquisition mode than in and a difficult operational during dense fog, etc.
This section should give a short introduction to operational aspects of AIS, functions and features, human aspects. The AIS transponder unit is designed to automatically broadcast the vessel's position, course, and speed over ground, together with static and voyage-related information. After activation, an automatic built-in integrity test, or BIIT, is performed. In case of malfunction, an alarm is given and the unit should stop transmitting. All AIS units are designed to communicate with each other automatically, exchanging information about course and speed and intended route. This enables the mariner to be aware of other ships long before visual contact is established, allowing appropriate action to be taken in good time. The master shall keep AIS in operation at all times, except where international agreements, rules, or standards provide for the protection of navigational information. If the master decides to switch off the AIS, this should be logged in the ship's logbook. The OOW should periodically check that the information transmitted by the AIS is correct. The information transmitted by AIS can be divided into three main groups: static, dynamic, and voyage-related. In addition, safety-related messages could be transmitted when needed. The static information provided by AIS is set on installation and consists of the following own ship data: Maritime Mobile Service Identity, MMSI, call sign and name, IMO number, ship's length and beam, type of ship, and location of positioning fixing antenna. The dynamic information, except navigational status, is automatically updated by AIS. The dynamic data may consist of the following parameters: ship's position with accuracy indication and integrity status, position time stamp in Universal Time Coordinated, UTC, course over ground, speed over ground, ship's heading, navigational status, and rate of turn. The voyage-related data must be manually entered into the system from the operator's panel and may consist of the following parameters: ship's draft, type of cargo, destination and estimated time of arrival, ETA, route plan, and short safety-related messages. The technical status of the AIS is checked automatically by the built-in integrity test, BIIT, but the quality or accuracy of the ship sensor data input to the AIS is not checked by the BIIT before being transmitted to other ships and shore stations. The officer on watch, OOW, should therefore carry out regular routine checks during the voyage to validate the accuracy of the information being transmitted. The frequency of those checks needs to be increased in coastal waters. AIS information can be displayed in various ways, such as minimum display, as alphanumeric information only, or any other suitable device such as radar, ECDIS, ARPA, etc. These symbols are recommended by the International Maritime Organization, IMO, for use with the graphical presentation and display of AIS target data in standalone or integrated navigational systems. The symbols may be changed at a later stage, after experience has been gained. A sleeping target symbol indicates the presence and orientation of a vessel equipped with AIS at a given location. No additional information is presented until activated, thus avoiding information overload. This symbol represents automatic or manual activation of a sleeping target for the display of additional graphically presented information, including a vector, speed and course over ground, the heading, and rate of turn, ROT, or direction of turn indication, if available, to display actually initiated course changes. This symbol represents the manual selection of any AIS target for the display of detailed information in a separate data display area. In this area, received target data, as well as the calculated CPA and TCPA values, will be shown. The dangerous target symbol represents an AIS target, activated or not, and indicates which data contravene preset CPA and/or TCPA limits. The lost target symbol represents the last valid position of an AIS target at the time data ceased being received. The AIS symbols shall be similar to that provided by ARPA or radar as far as practical. When AIS information is made available for a graphical display, at least the following information should be displayed: position, course over ground, speed over ground, heading, rate of turn, or direction of turn, as available. Whenever the graphical display of AIS targets is enabled, the graphical properties of other target vectors should be equivalent to those of the AIS target symbols. Otherwise, the type of vector presentation, radar plotting symbols or AIS symbols, may be selected by the operator. The active display mode should be indicated. The presentation of AIS target symbols, except for sleeping or lost targets, should have priority over other target presentations within the display area, including targets from Electronic Plotting Aid, EPA, Automatic Tracking Aid, ATA, or ARPA. If such a target is marked for data display, the existence of some other source of target data may be indicated, and the related data may be available for display upon operator command. A common reference should be used for the superimposition of AIS symbols with other information on the same display, and for the calculation of target properties such as TCPA, CPA. If AIS information is graphically displayed on radar, the equipment should be capable of approximately stabilizing the radar image and the AIS information. If AIS information is graphically displayed on radar, the equipment should be capable of appropriately stabilizing the radar image and the AIS information. Target data derived from radar and AIS should be clearly distinguishable as such, and the mode of presentation should be indicated. When the display of AIS symbols is enabled, removing a dangerous target should only be possible temporarily, as long as the operator activates the corresponding control. If the course over ground, COG, and speed over ground, SOG, vector is shown, its reference point should be either the actual or the virtual position of the antenna. If zones, guard rings, or search areas for automatic acquisition are specified and activated, these should be the same for all targets, regardless of their source. Whenever the calculated CPA and TCPA values of an AIS target fall below the set limits, a dangerous target symbol should be displayed, and an alarm should be given. The preset CPA or TCPA limits applied to target data derived from different sensors should be identical. If the signal of a dangerous AIS target is not received within a specified time frame, a lost target symbol should appear at the last known position, together with an alarm. The lost target symbol should disappear after the alarm has been acknowledged. An automatic display selection function may be provided to avoid the presentation of two target symbols for the same physical target. If target data from AIS and from radar plotting functions are available, then the activated AIS target symbol should be presented, if the automatic selection criteria are fulfilled. Otherwise, the respective symbol should be displayed separately. The operator should have the option to make reasonable changes to the default parameters of automatic selection criteria. As far as practical, the user interface for operating, displaying, and indicating AIS functions should be equivalent to the other relevant functions of the navigational aid. Current ship bridges, with all their communication, navigation, and other equipment, represent a major challenge to the navigator. The risk of information overload is imminent, which is why many navigators question the value of the minimum keyboard and display type AIS. The solution to this AIS problem seems to be a graphical presentation of the AIS target data.